Welcome to this Vector Medical Tuesday session on testing complex lab automation solutions. I'm Manuel, Customer Strategy Consultant at Vector, and for today's session, I'm joined by an expert engineer and a dear friend of mine. Thank you for being here.
Hi all, it's my pleasure. I'm Juanes. I'm a product engineer at Siemens Healthineers. Together, we will share some insights on how we collaborated to apply system-level virtualization and automated testing to simplify and accelerate the development of the Atellica solution. Since the Atellica is super complex, we will focus on an illustrative subsystem as an example to demonstrate our workflow. The session outline looks like this. We will give you an introduction to the Atellica solution. We will take a closer look at the example subsystem. We will introduce our system-level test tool, CANoe, and we will present our test concept, reveal some implementation details, and finally give a brief summary and outlook. The global demand for immunoassay analysis is ever increasing by aging populations, chronic disease prevalence, and regional infectious disease surges. At Siemens, we are determined to improve healthcare services and make them available to everyone. This can only be achieved by making diagnostics faster, more reliable, and cheaper. With years of experience and expert engineering, we have developed the Atellica solution, a highly automated platform for clinical chemistry and immunoassay testing. Immunoassays quantify target analytes via antibody-antigen interactions in healthcare. They play an important role in infectious disease diagnostics, oncology, autoimmune profiling, and endocrine assessments and therapeutic drug monitoring. Beyond clinical use, immunoassays play an important role in food safety, environmental monitoring, and pharmaceutical research. The breadth and clinical impact of these applications motivate robust automation to ensure accuracy, timeliness, and scale. Here, scaling is particularly important due to the increasing demand. Market analysis project continued growth for immunoassays, underscoring the need for high-throughput systems, such as the Atellica. Different laboratories have different amounts of space and different needs. So, with its modular architecture, the Atellica supports multiple physical layouts, I, L, and U shapes, which makes the system more flexible at the cost of increased development and integration efforts. Up to 10 components can integrate transport, processing, and analytics. This modularity offers a high degree of flexibility, allowing the Atellica to adapt to diverse laboratory layouts. The Atellica integrates all modules within a unified transport and control framework. The MagLine sample transport provides advanced bidirectional variable speed sample movement of STAT samples to analyzers. The Atellica IM1600 supports up to 440 immunoassay tests per hour, and a broad assay menu covers routine and specialty testing. For such a complex system to function reliably, a clear hierarchy is necessary. At the top, a Windows PC runs the user interface. The device management layer below is based on an RTOS controller and orchestrates the subsystems via a CANoe network. This device management layer handles the logic for all submodules and is the device we want to test. Multiple discrete control modules receive their instructions from the device management layer and integrate the sensors and actuators. One of the discrete control modules operates the cuvette loader unit, which is responsible for sorting and orienting cuvettes from a bulk bin into a precisely aligned channel for insertion into the incubation ring. Inside the cuvette loader unit, the cuvettes are lifted by a hopper chain, slide down a chute, they drop into a cavity, and are advanced into a channel by a pusher. This flow is simple in concept, but subject to manufacturing variability, since both cuvettes and the chute are injection molded. This leads to somewhat stochastic behavior. In the worst case, jams can occur within the chute. To resolve these luckily rare jams, the kicker unit applies controlled impulses to re-establish the flow, while the DML evaluates sensor feedback to determine whether the jam has been resolved successfully. In reality, these jams are rare. They occur about once in 50,000 cycles and are difficult to reproduce on physical systems. Waiting for natural occurring jumps is impractical, and manual propagation is time-consuming, tedious, and does not provide true consistency. When a jump finally occurs, the key questions are which sensor inputs should be used to register the jump, and how should the kicker be activated to resolve it. Clearly, relying on chance or manual effort won't get us far. With this in mind, we were looking for a solution to our problem. Maybe Vector, as a testing tool provider, can help us.
Of course, Siemens Healthineers needed a tool to simulate sensors and perform automated tests that in combination reliably provide a controlled environment for the cuvette loader. Let me introduce our system-level test tool CANoe. CANoe is a software tool developed by Vector, used for the development, testing and analysis of embedded devices and networked systems. It is used by embedded engineers in various industries, such as automotive, medical technology, railway, avionics, industrial automation, and other domains. CANoe supports the simulation of entire networks or individual devices, automatic test execution for function, safety, and security. It allows engineers to monitor and diagnose network communication. Why did we suggest an environment simulation in CANoe to Siemens Healthineers? First and foremost, it reduces hardware dependency. For example, provoking cuvette jams manually inside the machine using a pipette is tedious work. It is time-consuming and expensive. Moreover, it requires exclusive access to the machine, so other engineers can't use it at the same time. Instead, the counterparts of the system are simulated in CANoe, and this virtualization is used to test individual devices. Rather than having sensors and actuators as real hardware, we move them to the simulation tool. The system under test receives the sensor signal without knowing that the signal had been created virtually. In this approach, we benefit from all the advantages that simulations bring. For example, due to replicating various components within a virtual environment, we do not need physical devices for those components. This way, we can save hardware costs. This is especially relevant when the individual components are developed at different sites or during supply bottlenecks. By reproducing the complete environment in a single simulation tool, debugging becomes much simpler, as all events share the same time frame as the virtual participants are synchronized. Obviously, this approach is not limited to 2 or 3 participants and only a handful of signals that are transmitted between these participants. A complex network of control units, sensors and actuators can be replicated in a virtual environment. This allows test scenarios from testing of individual devices or modules up to the intricate interplay of multiple components. And these tests can be executed even before all hardware components are available, and bugs can be detected at an early stage during development when they are much cheaper to fix. Fault injections are much simpler because the behavior of the simulated component can be adapted more dynamically. Unexpected or incorrect signals can be sent at any time, and faulty behavior can be achieved with the click of a button. CANoe also helps you to automate your tests. Automation reduces manual effort, improves repeatability, and integrates well with CI/CD pipelines. The first part of the name originates from the CAN bus, but meanwhile CANoe supports a wider range of bus systems and protocols, including CANopen, Ethernet, SDC, MQTT, serial interfaces such as UART, digital and analog I/Os, and many, many more. When working with the Atellica system, Siemens Healthineers encountered several practical challenges. Multiple developers are working in parallel on different modules that interact with the device management layer, our system under test. Hardware availability is limited, meaning not every developer has access to the full system at all times. Certain scenarios are difficult to reproduce reliably on physical hardware. However, the modular architecture of the system also gives us significant advantage. Each DCM operates independently and processes commands from the DML in isolation. This modularity greatly simplifies the development of simulations. In the simulation of the cuvette loader DCM, we have complete control over all parameters. We can reproduce standard workflows such as having a cuvette loaded by the hopper chain, sliding down the chute, and being inserted into the channel by the pusher. We can also trigger unusual edge cases, like a cuvette getting stuck inside the chute, and even inject specific faults, for example a sensor malfunction, to verify how the system reacts. Another major benefit is shareability. Once a simulated component is created, it can easily be passed on to different development teams. They can integrate it into their own environment simulation without requiring actual hardware. Let me now trace the actual steps to go from manual testing to a fully automated solution. The first step is to simulate the cuvette loader in CANoe. Within the simulation, we don't need to reproduce every detail of the system. Instead, we focus on a targeted subset of its functionality, specifically the logic required for communication with the DML. Sensors, actuators, and other physical components can be included in other scenarios. In parallel, the DML itself is simulated too. By having both sides available in a fully virtual setting, we remove any dependency on real hardware. This gives us space to experiment, understand the communication flow in depth, and even detect missing or unclear requirements very early on. With these simulations in place, we can already begin developing automated test cases that validate the basic communication and logic. As a next step, the DML software can be executed on the host PC instead of the actual DML hardware. This allows us to thoroughly validate the software logic in isolation. Importantly, the test cases we developed in the simulation phase can be reused directly, ensuring consistency and saving efforts. This setup is called software-in-the-loop testing. It is not strictly required, but can help us to catch issues early on. Finally, the communication takes place over the real CAN bus via a vector network interface. Again, we can rerun all previously created test cases, and we can now extend them to include verification of the hardware-specific drivers and interfaces. This is called hardware-in-the-loop testing. We can also imagine a reverse scenario, using the simulated DML to test the DCM. In this setup, CANoe can simulate sensors and actuators and connect directly to the DCM controller. The VT system provides the hardware interfaces needed to emulate the physical environment around the DCM. But let's get more specific. Juanes, can you tell us how you started to simulate the cuvette loader DCM?
Sure, that was quite easy. Since I already had the device configuration files, or DCF in short, I could simply import them into CANoe, which in turn provides a dedicated variable for each object dictionary entry. Therefore, the low-level data structure was created within minutes. To finalize the simulation, I implemented the logic which maps the high-level expressions to low-level operations. For example, the kicker receives commands like cuvette kicker extend and provides information by sending the events event cuvette present at kicker or events cuvette not present at kicker. These expressions are the ones that will later be used to implement tests. They are much easier to understand than the low-level CANopen message payloads. Much of the internal actions of the system can be modeled by using timers, which facilitate and accelerate the implementation. When I run the simulation and trigger an event, I can look into the trace window. The purpose of the trace window is to record activities during measurement. All the messages received are displayed as lines of text. Both the low-level traffic on the bus and the high-level interpretation with the same timestamp are shown. This correlation of protocol frames with domain semantics makes debugging much easier. On top of that, I created a custom panel. In CANoe, panels are graphical elements via which values can be changed and displayed using so-called controls. My panel displays all parameters that are important to me. I can also use it to conveniently trigger events or tweak some parameters while the measurement is running. Being able to reproduce very specific operating conditions allowed us to figure out minor software changes that greatly reduce the probability of jams occurring in the cuvette loader subsystem.
Integrating CANoe enabled Siemens Healthineers to greatly reduce the hardware dependency and accelerate the development process. This directly leads to improved product reliability and quality. Looking ahead, we will extend component virtualization and incorporate more complex hardware-in-the-loop tests, including sensor and actuator simulations. Thank you for joining us today.